Okay, thanks everyone very much for coming. My name is Yuri Levin. I'm an astrophysicist here at Monash. And it is my pleasure today to introduce our speaker at today's public lecture, Professor Christopher Matzner, who is visiting us from the University of Toronto and who is an old friend and colleague and collaborator. Chris did his undergraduate degree at Harvard University and then went on to do his PhD at Berkeley, where he graduated in the year of 2000. Then he went for postdoctoral work. He did postdoctoral work at the University of Toronto in Canadian Institute for Theoretical Astrophysics. Did many interesting things there, and they loved him so much in Toronto that they asked him to stay for a faculty position. So he's been a professor at Toronto ever since. Chris is really a broad theoretical astrophysicist, but he's worked in particular on the topic of the birth of stars and the death of stars. So neatly, kind of cuddling the extent of life of, in particular, massive stars. But today, his topic is a bit different. He's going to talk about something which is not a very commonly forms the core of astrophysical research in modern departments, but nonetheless is a very interesting and important topic. He's going to tell us about interstellar messaging. Please.
Thank you. Thank you. Well, it's excellent to be here, and I'm very glad to be in Australia, and I'm really enjoying a 4 or 5 month visit, which I'm unfortunately coming to the end of. I'm very happy I could spend this time with you talking about an interest of mine, which involves not the birth and death of stars so much as the life of civilizations like our own. And so what I want to talk about is a talk that covers a fair amount of ground, going from how we might find extraterrestrials in the galaxy, to how we might communicate with them, to how we ourselves might become extraterrestrials and get off of the Earth and the solar system. And this is a topic that goes way back to much earlier times, when there were speculations about life elsewhere in the galaxy. So I want to organize it in 3 parts: the past, the present, and the future. And I'll start off with a brief review of how we got to where we are today. The notion that there might be life elsewhere in the galaxy or elsewhere in the universe actually goes back at least as far as the Greek philosophers. The atomists had this idea that the universe was infinite. And so you have quotes surviving from that time, like this one from Metrodorus of Chios, 4,000 years BC. It is unnatural in a large field to have only one shaft of wheat, and in the infinite universe, only one living world. So this idea that we were not alone was already with us, and that the idea persisted. So a few centuries later, in the Roman times, Titus Lucretius Carus issued a very similar quote: nothing in the universe is unique and alone, and therefore, in other regions, there must be other Earths inhabited by different tribes of men and breeds of beasts. And the implication was that it wasn't just new places for the Roman Empire to conquer, but in fact, farther afield. Although I think the notion of how far afield you might have to look wasn't very clear at that point. So in the 1500s, in the early 1500s, this fellow made a very important contribution to thinking about our place in the universe. This is Nicolaus Copernicus, and what he did, many of you are aware, is that he argued that the motions of the planets were poorly described by a system in which the Earth and our civilization is at the center of the universe, with everything else orbiting around it, and was much better described by a heliocentric system, one with the sun in the center, with the planets orbiting around the sun, and ours being the third one out. And this was just a devastating demotion of our place in the universe relative to where we had been assumed to be prior to that time. There had been some previous suggestions that we might not be at the center of the universe, but this is the one that has caught on and led to a revolution in our understanding of our place in the universe. And you can really draw a line from Copernicus's revolution that takes us away from the center of everything to a modern understanding of physics and cosmology in which our own perspective is not especially privileged. So from that time on, well, the notion that there might be life elsewhere was taken up again, for instance, by this Italian monk, Giordano Bruno, who echoed a quote very similar to what the atomists had said about there being multiple worlds with other Earths around them. Unfortunately, at this time, the Catholic Church was not especially receptive to that notion, and you can guess what happened. Right. So moving ahead a little bit, in the Enlightenment period, this notion really took off, and people started thinking about the idea of life on other worlds rather seriously. There was speculation by writers, philosophers, and scientists on what came to be known as panspermia, or what had long been known as panspermia, the idea that life might be widespread throughout the universe. And in about the 1820s, it was suggested that we might actually get in touch with life elsewhere in the universe. So Carl Gauss suggested that we should demonstrate how clever we are here on Earth to the Martians by creating a demonstration of the Pythagorean theorem, because really, what demonstrates your intelligence better than a reference to Pythagoras? And then Joseph von Litoral suggested that we amp it up a bit with some kerosene and create some giant illustration of how well we understand the universe through the Pythagorean theorem. The modern view started developing at about the same time during the Industrial Revolution. So William Whewell sounded a cautionary note, saying that really we shouldn't expect everywhere in the solar system to be inhabited with life. I mean, you have these outer planets. They're very far from the sun, so they're probably they're gas giants. They're probably very cold. And the inner planets, well, they're very hot. And so perhaps we are in a sort of privileged position after all. And that notion that we're in a somewhat privileged position with, on a habitable world is one that has stuck with us. And we now look for habitable worlds around other stars. Around the turn of the turn of the previous century, one of the early rocket scientists, Konstantin Tsiolkovsky, made an extremely important observation. He said, well, humans have been developing for a long time, and we will presumably be developing for a much longer time. So why should we expect to see extraterrestrials at our own level of development? Why shouldn't we expect that they're actually way far ahead of us in some cases, or way far behind in others? There was more activity in the trying to get in touch with aliens once radio technology was developed by Tesla and Marconi. Tesla sent out a pulse of radiation which apparently strained the electrical resources of Colorado Springs, Colorado, and then, waited for a reply. And Marconi thought that he actually heard a burst of radio waves. These are two of the pioneer developers of radio technology. This notion of panspermia was discussed around the same time by a Swedish chemist, Svante Arrhenius, who suggested that, in fact, there were spores flying between planets and flying between stars that would seed life, and that we ourselves might be the result of one of those events. And this notion was kept alive by the late great astronomer Fred Hoyle, because essentially because it was consistent with his view of the universe as being infinitely old, and that would give a lot of time for spores to move around the universe. In fact, in 2003, there was an epidemic of a virus called SARS, and the notion that life might be propagating itself throughout the universe showed up in news articles, although I think many people, almost everyone, had stopped taking it very seriously at that point. Okay, so I'm just going to draw a line in the past at this point, and start talking about where we find ourselves today. So before I do so, is there any comment or question? Okay, so the present. So understanding the universe is obviously much sharper and clearer now than it was in even 100 years ago. And I want to focus on a couple ways that our understanding of our place in the universe is sharper. In one way is, of course, where we find ourselves in the universe. And another way is, well, one of the many other ways, is how we understand our position within the history of life on Earth. Okay, so first, where do we find ourselves out in the universe? Okay, so this is our planet. That's the Earth. It seems like a big place, right? But it's not that big. You can pick up the phone, and you can call your great aunt in some other country, some other continent, all the way around the world. And if you think about it, the reason that that's possible is that our planet is really quite small compared with the speed at which light travels, which is sort of close to the speed at which telephone signals go at this point, now that we have fiber optic cables. And in fact, light can go all the way around the Earth 7 times a second. So when you pick up the phone and call your great aunt, it's not going to have a huge delay. So our planet is big enough to hold 10 billion individuals, clearly, but not humongous. How about the solar system? We live on, this is kind of dark, isn't it? This is the Earth in red, that's the sun, and this is an illustration of the paths of the planets. And the size scale of this diagram is light can go from one side of this diagram to the other side of this diagram in about the length of my talk. Okay? So the solar system is big enough to cause a significant delay in your phone calls with your loved ones, but you're still going to be able to make that call. If we go about 100,000 times farther out, we come to the nearest stars. Okay, so now the solar system is that red splotch down in the middle, and this diagram is a few decades across in terms of the travel time of light, and big enough that we might be able to send a signal out and get a signal back before we get too much older. But then the local neighborhood of stars is really just a small splotch in the much larger structure that is our Milky Way galaxy. So this structure has about 100 billion stars in it, about 10 stars for every person alive today, maybe a bit more. And the time it takes light to get from one side of the Milky Way to the other is something like 100,000 years, and that's comparable to the time that modern humans have been modern humans. The Milky Way galaxy is a smaller part of a local group of galaxies. There's the Milky Way, there's the Andromeda galaxy. If you look up in the sky from the southern hemisphere, which I hope you do, you should see the large and small Magellanic Clouds, which are orbiting our galaxy, and we are part of this larger group. And then if you go a little bit farther out, you get to the Virgo supercluster. And the Virgo supercluster is part of an aggregation of local superclusters of galaxies. So this is clusters of galaxies. And then as you go even farther out, you come to the size scale of the observable universe, which is really defined by the fact that the universe began, it appears, 14 billion years ago and has been expanding ever since. And so when we look, for instance, in a simulation of the structure of matter in the universe, what we see is that on large scales, it's pretty much the same in all directions. It's, we would say, homogeneous and isotropic. And this is Copernicus's principle written on the scale of the entire universe. We could be anywhere in this diagram, almost, some little splotch someplace, with the exception that, of course, we're alive, and we're on a planet, and therefore our position has to be a little bit privileged. We have to be in one of the places where the matter distribution of the universe has been accumulated by gravity, so that stars and planets and galaxies have formed. Okay, so that's our position within the universe. And it's important to realize that, there are about as many galaxies on the sky as there are stars in the galaxy. And so, and like I said, that's about 10 for every person alive today. Okay, so then another way in which our view of the universe has gotten far sharper, of course, is our understanding of the history of the Earth and life on it. So this is a diagram of the history of the world, stolen from Wikipedia. So this is the beginning of the universe at, the dawn of the Big Bang 14 billion years ago, and its evolution in time. First, cosmic evolution, and then the evolution of the Earth. And what you see on this diagram is very striking, if you look carefully. Okay. So what you see is, first of all, you see that the solar system and the Earth are about half the age of the Milky Way galaxy and about a third the age of the universe. So as a planet goes, we are not forming late or early in the evolution of the universe, but kind of in the middle. And then another thing you notice is that life starts very early here in the evolution of the Earth. In fact, it's almost the case that the earliest rocks that we have left over from the earlier portions of the Earth's history show signs of life. So life starts really early on a planet. And this is the only example we have, but in the one example we have, there's life about as far back as you can find. And then the third thing, of course, is that here we are now in, what year is it, 2016. There we are at the very top, right? We are a minute sliver in time compared with the several billion years that life has persisted on Earth, which is not a small fraction of the history of the universe. So what it looks like on the diagram, and there's debate as to how far you can push the one example that you have. But what it looks like on the diagram is that life got started really early in this one spot that we have, which is really habitable. And yet it took a really long time to get to our state and become like us. So that might tell you something about what you expect to find out in the galaxy. Okay, so let me talk for a moment about what we might expect to find. So people, astronomers and people looking for extraterrestrial worlds and extraterrestrial intelligence tend to look close by in the Milky Way. Why? Because the Milky Way is this big agglomeration of stuff pretty close to us, and it's the nearest stars are in the Milky Way, and once you get outside the Milky Way, the distances are just too far to imagine communication, for instance, or travel. Okay. Now, what do we expect to find? So this is an old question, and you've probably heard a little bit about it, but the question of what we expect to find around us is usually discussed in terms of this equation, which is really just a list of unknowns. Well, some of them are known. But it's a list of what we know and don't know about what would lead to life trying to get in touch with us from elsewhere in the universe. It's called the Drake equation. It was written down in a meeting by Frank Drake in 1961 after a brief unsuccessful search for signals from other worlds. And it goes like this. So basically, what you want to know, which is on the left-hand side, is the number of people sending you signals right now. Number, I shouldn't say people, three-eyed bug creatures trying to send us signals. And it is broken down into factors. The first factor is the average rate at which stars have popped into being in the course of the galaxy. So that's the number of stars divided by the age of the galaxy. We know that number very well. It's something like 10 stars a year. And then there are things we don't know, especially back in 1961. How many of these stars have planets? How many of the planets are anything like the Earth? And you could imagine that they would be hosts for life. How many of them actually are habitable and capable of starting life and then do? What fraction of those go on to produce intelligent life? What fraction of intelligent life could be octopuses, could be dolphins, could be magpies. I don't know if you've noticed how intelligent they are. But they haven't been broadcasting in radio waves, and so the next factor has to do with what fraction of intelligent species actually goes on to broadcast radio waves. And then the last factor is how long do they keep at it? And that's very important because the first factor was a number per year, and the last factor has to be a number of years to cancel that out and give you a pure number. Okay, so the 1961 view of this equation was, considering pretty optimistic numbers for all those things, that the number of civilizations beaming to us in the Milky Way right now is equal to, or roughly equal to, with very big uncertainties, roughly the lifetime of a civilization measured in years. It's a very simple story. If you're going to have the typical civilization lives for 1,000 years, then there's 1,000 of them beaming radio waves at you. If they only live for 20, there's only 20. And if there's only 20, it's really hard to find another one in the Milky Way, as I'll show you in a minute. Now, this was a very important equation when it was written down. This was the height of the Cold War. And so, of course, everyone was worried that it might not, the number of years might not be that big. I think that we have gotten past most of the problems that we had in the height of the Cold War, but there are definitely things to worry about, which I might come back to later. So what has been changing? One of the things that's been changing is that we have been searching for other examples of life on other worlds. If it was so easy to start life on Earth, then perhaps it was easy to start life on Mars. Mars now, it's clear, had water and was warm back in its early evolution. So maybe there's evidence of past life there, or there is still life maybe beneath the surface on Mars. And a recent result, this is the Curiosity rover, a recent result from the Curiosity rover was that there was a verification of a signal that had been seen from Earth and was disputed for a long time, that in fact there is an outgassing of methane coming from below the surface of Mars. And methane is very interesting. First of all, methane doesn't last very long in the Martian atmosphere. So methane that appears in the Martian atmosphere has to be coming from someplace. And secondly, there are only a couple of ways that methane is thought to be produced on Mars, and one of them is subterranean microbes. Unfortunately, there are other ways it could be made. Another thing that's been happening, you've probably heard about, is that we've been finding bucket loads of planets around other stars using a few different techniques. Primarily these days using the technique of watching stars pass in front of their suns. And so now here is the location of the Earth in terms of the number of days it takes to go around and the size in units of radii of the Earth. And you can see that this technique, the stars passing in front of their suns, is not sensitive to the actual Earth, given the data that we have from the Kepler satellite. But given the distribution of planets that in the parts of this graph that you can see, it looks like there ought to be a lot of Earth-like planets out there. And in fact, there are some really striking examples of people finding systems of Earth-like planets, for instance, around smaller, dimmer stars than the Sun. And I just saw a preprint today saying that there's about 5 planets per star. So that gives you a sense of how teeming the galaxy is with planets. They're not all like our own. Many of them are not like the Earth, but some of them are. And okay, so now let's talk about finding these planets around other stars. The history here is kind of checkered. I'm not going to go through it all, but basically there has been an effort to look in especially radio and optical signals, to look for signals from other civilizations. And you can actually take part in it. This is a screenshot from a SETI at Home, the SETI at Home application, which is something you can download and then use on your computer to search through data for signals from other worlds. I should mention, of course, that searching the sky for signals from extraterrestrials really relies upon having some sense for what they might be sending you. And we've been looking for the things that are easy to find, which basically means we've been looking for a present from extraterrestrials. That they know we're here, or suspect we might be here, and they're sending us radio signals. So that doesn't have to be true. Now, people have also started sending signals out into the skies. I had the opportunity, actually, to compose one of these. This is a signal that did not actually get sent with a radio telescope, but it was sent to a group of humans who were the students of a friend of mine. He was teaching a class at the University of Michigan. His name is John Monnier, and he asked if I and my friend George McLean would come up with a signal to stimulate discussion in the class. So we came up with a radio signal, and we described its frequency and such. And this is its form in binary. Now, if I take the signal and I move it, you can see what the encoding is. Let me just do this. You can't see that. Okay, well, I think as soon as I do this, you'll be able to see it again. So I put it into a particular format where I change the width. And what you can see here is that it's a sequence of bits. The sequence of bits is a square, and the number of bits on a side is a prime number. And this is a standard way to encode messages, long strings of bits, as two-dimensional images. If you rearrange them the right way, you see a picture, which hopefully you can see here, is is a circle. Now, we actually went farther. We tried to see if we could communicate thoughts to these Michigan students. So we put together a message which looks kind of complicated. It's got numbers, it's got sentences. The sentences are true or false, and then they send information about our symbols and what we're trying to say. And I'm pleased to say that the Michigan students actually were able to decode our message, most of which was math, but we started sending information about things like the size of our planet. So I'm very happy that this was successful. So this is very similar to a message that was sent by Frank Drake in 1963 towards the M31 globular cluster, which looks like this. It's, again, a long string of bits sent from the Green Bank radio telescope. And what it's got numbers. It's got the atomic numbers of the elements in life: carbon, nitrogen, oxygen, hydrogen, and phosphorus. And then it's got the amino acids that are built from those things. It has a description of DNA molecules. And it has other information like which planet are we on, that's the Earth, what's the size of the radio telescope, et cetera. So this is the first of a number of signals that has been sent out. Okay. Now, actually, there's a number of signals that have been sent out, and the signals nowadays include things like messages composed by teenagers and messages composed on social media. So nowadays, you can personally take part in composing messages to outer space, but this has prompted a certain backlash from some of the scientists who have been looking for messages, because once other people start sending messages out into extraterrestrial space, they start to get worried that we don't know what we're sending out there to aliens, and maybe we should worry about it. Okay, so that's, I'm going to stop with the present now and go on to the future. Okay, so let me just finish up by talking about what the future holds or might hold regarding the search for signals from outer space. One of the things you can do, if you think about the structure of the galaxy we live in, and you take a sort of optimistic view of Drake's result, Drake's equation, and assume that the number of civilizations beaming at us is about the lifetime of a civilization in years. Well, what does that mean? It means that the longer we last as a civilization, the more people we are likely to have access to. And past a certain point, that combination means that you're going to live long enough to get one of the signals. And past another point, it means that you live long enough to actually hold a two-way communication with the aliens. And given the structure where we find ourselves in the Milky Way galaxy, the break-even point for holding two-way communications is a couple of millennia, sort of the duration of the Roman Empire. So if we can hold on as a technological civilization longer than the Romans held on to their empire, then we're doing pretty well, and we might actually then expect to hear something from another civilization. Well, how about spreading humanity across the galaxy? The galaxy, like I said, is really big. It's 100,000 years for light to travel across the galaxy. But keep in mind, the galaxy is also 10 billion years old. So 10 billion years is a lot more than 100,000 years. And what that means is that if you can make a rocket that's going to go a tenth the speed of light, you can actually get across the galaxy 10,000 times in its age. So you can start to think about propagating humanity, or whatever you're propagating, across the galaxy. You can think about moving from planet to planet, star to star, world to world. And even if you're going relatively slow, 30 kilometers a second is slow in this game, although it's much, much faster than the speed of a bullet. even then, you can get back and forth in about 10 times in the age of the galaxy. So at this point, I think it might be appropriate to just mention that something you may have heard in the news media, which is this object. Now that we can view the sky with satellites like the Kepler satellite and with many people's telescopes, we find all sorts of weird stuff, right? And this one has caught people's attention because it's pretty weird. This is a star with hard to explain dips in its brightness. And they act strangely. They go down and they go up suddenly. It's somewhat unusual. Some people have suggested that this star could be the remnant of could be surrounded by an alien civilization or the remnant of something that they built, and that's what's giving this dips in brightness. I'm sure much more mundane explanations have to do with things like comets around the star. Okay, so can we get off of the Earth and become extraterrestrials? Okay, this boils down to rocket science, and I told you that you can get back and forth across the galaxy pretty fast if you can move. So can you move? Rocket science is the question of whether you can move and how fast you can move, and it's pretty simple. It boils down to this. If you have a big thing you call a rocket, let's imagine that in the middle of it, let's start off sitting still in space. In the middle of it, you put a big spring. And the spring stores energy. And if you set the spring off, it moves the two halves of the rocket away from each other. Let's say it's such a really strong spring, and it can move the two halves of the rocket 10 kilometers per second away from each other. That's really fast. I wouldn't want to be in the cockpit when that happens, but let's just imagine that it could happen. Well, what would happen then? Well, then two halves move away from each other at 10 kilometers a second. If they're equal mass, then one of the things we learned from Newton is for every force, there's an equal and opposite force. So momentum is conserved. And what that means is that the front half will go 5 kilometers per second this way, and the back half will go 5 kilometers per second that way. And we've got the front half of the cockpit of the rocket moving 5 kilometers per second by throwing away half the rocket. If we want to go faster than that, guess what? We have to split the rocket again and send the first quarter of it, and we can get that going 5 kilometers per second faster. Every time you split the rocket in half, you get the front half going an additional 5 kilometers per second. And what that means is that you quickly run out of rocket, especially if you want to speed up and then slow down again. This is very similar to what happens if you actually have fuel in the rocket and send it out the back slowly. It's essentially the same thing. So what it tells you is that it really matters what kind of fuel you use to do your traveling. And the type of fuel sets the speed that you can move the rocket at. If you're going to use chemical fuel, then the best chemical fuels like hydrogen and oxygen can go out the back of the rocket about 4.5 kilometers a second, which sounds fast until you realize that that is below the speed you have to get off of the Earth. So if you want to get off of the Earth, you're kind of lucky you can do it at all. And this is why we have to use multi-stage rockets to get off the Earth. And at that speed, to get to the closest star, which is Alpha Centauri, would take tens of thousands of years. You can actually do a little bit better by, at this speed, to get a little bit of more speed, you can run your rocket past Jupiter, use a gravitational slingshot, and that gets you up to something like 20 kilometers per second, which is definitely better than 4. Okay, so, but that's still kind of pitiful. What about if we now start thinking about much more energetic things like nuclear reactions? There's a lot more energy wrapped up in the nuclei of atoms than in their electrons, and so the amount of energy available in nuclear fuel is much, much larger than the amount of energy available with chemical rockets. And this, with nuclear fission, you can get up to a few % of the speed of light, and you start getting to the nearest stars in about a few hundred to 1,000 years. With nuclear fusion, the fusion of hydrogen into helium, you can get really significant speeds. And then if you could ever hold antimatter and produce enough of it to do this, which is very, very hard, you could get up to speeds of order the speed of light. And then you could really get places really fast. Okay, well, so this sounds very dramatic and difficult to imagine doing. But in reality, it has been imagined, and it's been imagined ever since the 60s. So this is Project Orion. Project Orion was a concept developed by Freeman Dyson. And Freeman Dyson is a very notable physicist who was involved in this plan. And the plan was to hold a whole bunch of nuclear bombs, essentially in some designs like the entire arsenal of humanity, and instead of using it to blow ourselves up, send it out the back of this device and explode them back here. Because we don't have anything that can hold a nuclear bomb, but we do have materials that can withstand being that close to a nuclear blast. Once you do that, then if you have really good shock absorbers, really, really good shock absorbers, you can hold some large bunch of living things in the front and not kill them. It sounds absolutely crazy, and it is crazy. It's really crazy. But it's not as crazy as you might think it is. So here's an example. Okay, one of the crazy things was that they actually thought about launching this from the ground. And if you think for a moment about what would have happened if they launched this from the ground, I think you can see why that was crazy. Wait, what's going on here? Is this going to run? Okay, this is a demonstration. This is not a nuclear blast. This is a demonstration that the design kind of works. This is a bunch of essentially grenades being shot out the back of this structure and launching it up a few hundred, 100 meters into the air. One of the things about the Project Orion craft, which is really, it's not the only interstellar spacecraft design that I've heard of, but it's the one that seems most practical because it uses stuff we've already got. One of the things about it is that these explosions are so big that you wouldn't send a small craft this way. You would send something humongous. You would send something like this fantastical picture of a space ark where there's a cylinder taking entire ecosystem from one planet to another. And you have, this is a bit big, but you do have enough nuclear bombs, at least at the height of the Cold War, to consider doing this. Now, the only problem, of course, is you have to send a viable ecosystem that's going to last long enough to go to the place you want to get to and establish itself somewhere else. Our only example of trying to hold an ecosystem inside of a closed enclosure is the Biosphere 2 experiment in Arizona. And if you know anything about how that went, it wasn't pretty. So overrun with ants and problems with oxygen and all sorts of things. It's not good. So we would definitely need to be a bit more on the ball about it than that. It's a good time to mention that there's been a recent announcement of what's called the Breakthrough Initiatives, which is where Yuri Milner and with Mark Zuckerberg and Stephen Hawking, they've got 3 plans that they're going to try to put into action. One is called Listen. It involves listening for signals from other worlds. One is called Starshot, and so I'll mention Starshot in a moment. One is called Message, which involves sending signals out into other planets. So this is the Starshot component. The Starshot component is not sending humans, but instead involves blasting a small sail, reflective sail, or a number of small reflective sails, with lasers from the ground, focused on about a square meter and very light structure, which will then pick up momentum from the light itself and accelerate away from the Earth at almost a sixth of the speed of light. And at that speed, the idea is to send these structures off to Alpha Centauri and then hopefully get a signal back from them about what it's like over there. Of course, they won't be able to stop. unless they are successful enough to actually hit the star. Okay, so at this point, it's worth thinking about what the future holds for us. So are we going to get away from the Earth? And if we do, what is going to get away from the Earth? This is a plot of the development of computer power over the last 50 years or so. And the increase in computer power is now, there are questions about whether Moore's law is trailing off, but the trend is for computer powers to reach the equivalent of human brains sometime in the next maybe decade and a half. So in that case, perhaps we shouldn't send humans, perhaps we should send robots. And I illustrate at the top, you might notice nowadays that there's a huge difference, you can see this increase in computer power, in the difference of what people are paying attention to on the subways now versus 1974. This is assuming, of course, that you can look up from your phone long enough to notice what's going on. So, so that's maybe where we're headed. Maybe we can get from Earth to another one of these many terrestrial planets in time to settle ourselves in and launch ourselves off from there to a new horizons across the galaxy. And hopefully we won't destroy too many young life forms in the process. But there's a note of caution that I want to end with. And this is called the doomsday argument. It's a somewhat depressing place to end your talk. So I'll try to keep it light. So the doomsday argument goes like this. It's a simple question. Suppose I have two urns, right? Two urns. They're beautiful. And into one of them, I put the numbers 1 to 10. And in the other one, I put the pieces of paper with the numbers 1 to 1,000. And I shuffle them up. I don't tell you which one is which. Okay, now, who wants me to take a number out of the right urn? Raise your hand. Okay, there's only 2 people, so it looks like I'm taking a number out of the left urn. I take a number out of the left urn. It is the number 7. Okay, so one of the urns had the numbers 1 to 10. The other ones had the numbers 1 to 1,000. I picked a number out. It's number 7. Okay, if I give you odds on this one being the one with all of the 1,000 numbers in it, are you going to take those odds? Or what odds would I have to give you for this one, for you to put down money on this one being the one with 1,000 numbers in it instead of the one with 10 numbers in it? It could be either, right? 7 is in both lists. But I think you'd probably bet on it being the one with 10 if you just got the number 7 out. Okay, now where does this take us? Now imagine that instead we list all the humans who will ever be alive. Okay, now I don't know how big that number gets, but my number and your number are all around 100 billion. There's close to 10 billion people on the planet right now, and about 1/8 of them have always been alive. About 1/8 of the people who've ever been alive are alive today. So our numbers are in the vicinity of 100 billion. And so if you think of, we have chosen from an urn the number 100 billion. Well, it would be very unlikely if we chose from an urn that had a number much more than 100 billion in it. So the proposition from Brandon Carter and J.R. Gott is that just because we woke up one day and found ourselves as the 100 billionth or so person alive, that makes it kind of unlikely that there's going to be trillions and quadrillions of humans that'll exist ahead of us. So it's a prediction about the future. So they're saying that the fact that we are alive today here suggests that humans are not going to colonize the galaxy, because if we were going to, we wouldn't have woken up one day on Earth. We would have woken up on a galactic civilization that we had started. It's a terrible thing to say, and I really resent it. So what do you think? I take the point of view that these guys do not know the future. And in fact, that anybody in human history could have made the same argument about humanity stopping in the next, in the next 20 years, basically. All of them would have been wrong, and I would suggest that we're also wrong. So at that point, I'll just leave you with that sobering thought, which really is a reason. It's really just a reason to pay attention to existential threats that you might see ahead of yourself. If you think that there's something that might go wrong on this planet, you should really do something about it and not assume that some future human will help you figure out how to persist into the future. Thank you.
Okay, so we have time for questions and discussions, please.
Do you think, on Star Trek freaking, do you think that we'll ever be able to travel seriously at warp speed? That was fast and speed of light.
I don't know. I'd say I don't. And the reason I don't is not because I place ultimate faith in our understanding of physics at the moment, but because if we ever got to that position, then this problem of not seeing other civilizations around us would just get vastly worse. Same with time travel. Yeah. And it's essentially the equivalent question. Yeah. Other thoughts? Yeah, that's a great point. I love it. So as long as we have no knowledge of the vast civilization, the argument fails. Also, if we were to change dramatically, for instance, becoming one with our iPhones in the next 30 years, that would also change the nature of the argument significantly.
Sorry, just to clarify, is your bottom line in contrast to Stephen Hawking's concept?
I'm not sure. I'm not sure exactly what Stephen Hawking thinks, to tell the truth. I know that Stephen Hawking thinks we need to get off the planet fast. And he says this is why he's in the background and on the board of the Breakthrough Starshot. He basically thinks we need to make it happen sooner rather than later, probably because he appreciates that doomsday argument and he wants to prove it wrong, I think is the answer.
Yeah, so looking for signals, you're always looking in the electromagnetic spectrum. And there was recently gravitational waves discovered. What would be the possibility, probably unlikely, but what would be the possibility that signals could be sent through gravitational waves?
It's an excellent question. I can't imagine a way it could happen, but Yuri can probably think of one. I'll just mention something else, some of the other ideas that Yuri has had. So Yuri Levin here has suggested that, for instance, if you're going to look for communications from other species or try to get someone else's attention. So people have suggested, well, the Earth is going around the sun, so that provides a natural sequence of stars that know about us. We go between the sun and them. So we should send out signals to broadcast our presence to them. And Yuri points out, well, they're probably actually looking at the galactic center, which is much more interesting than the sun, or they're looking at pulsars, which are very interesting. And so what we should really do is to send out signals in the other directions that are kind of like what the galactic center and the pulsars are doing, but play with their minds a little bit and show them that that we're here. So that's another suggestion. But when it comes to gravity waves, I'll leave it to the relativists.
You mentioned, Chris, about sending a deliberate signal into space, but we're transmitting signals all of the time.
Yeah.
Is it possible that other civilizations out there could be transmitting signals that we're transmitting?
Yes. Okay. And this brings me to this topic. So this is a topic that was worked out actually in 1973 by some undergraduate students at MIT, I think it was. It's the question of who can see our presence out in the galaxy. So we've been broadcasting radio signals for, well, since about 1940, and this is the distribution of radio power that we've been sending out. And what these people suggested was that planets who detect our signals, especially television and military radar, would be able to build up a picture of our, not just our civilization, our technology, but our location, our distribution around the Earth. What kinds of radio towers have we got? What kinds of languages do we broadcast in, et cetera? So, so the answer is yes, I guess. I don't know if that fully answers your question, but yeah, we are visible to the outside, to large radio dishes, out to the distance that these signals have propagated so far. You need really, really big radio dishes as the signals get farther away, and there are issues with the propagation of radio waves through interstellar space that make it hard to go all the way across the galaxy without meaning to.
Okay, this has got nothing to do with it, but like since grade 4, I've been puzzled about this. Why does the spelling of science fuck up the whole idea of I before E except after C?
I can't answer that question. Sorry. Sorry. One of the questions that I can't is beyond my pay grade, unfortunately.
I think Stephen Hawking's concerned about attracting hostile attention. What's your point on that?
That is something that has increasingly become a suggestion, and people have raised the possibility of hostile attention. The notion of hostile attention really rests on the idea that we have something that an alien species would want that they can't get otherwise. So they probably don't want to subjugate us, but they might want the real estate. So as long as there's a lot of nice real estate out in the galaxy, a lot of habitable planets, then I'm not so worried. If there's only a few, then you'd want to worry about it. But at the same time, if there's only a few, the chances of there being someone to be hostile to us is relatively low. Oh, it's excellent fodder for science fiction, yeah.
What relationship do you see between sustainability and our ability to colonize hostile planets, do long-term space travel, and spread out?
Well, the whole concept of having someone to interact with and of getting anywhere beyond the Earth rests upon the concept of sustainability and stability. You just cannot consider getting anywhere if you aren't an exceptionally stable species that takes care of its resources. Resources, you have to think very broadly. Resources includes things like the distribution of species that you want to have around you because you might need them, or they might wind up becoming the things that actually persist into the far future. So, so that's definitely worth thinking about, and it's an extremely important point. Yeah.
Yeah, just another quick question. What would be the first
I think I had it, but then I erased it because I thought it might be slightly offensive. So I still have it. So one of the first signals that actually was sent out was the opening, not the first, but one of the first broad, strong signals that was sent out was the opening ceremonies of the 1936 Olympics. And there was many of you know what there was. There was Adolf Hitler and the Nazi salute going on in that first broadcast.
That brings me to the next question. How true to reality is Carl Sagan's book and the film concept?
Okay, I've read the book and I've seen the film. It's been a while. Which aspects? Yeah, okay. So, well, I think, there's a hypothetical future in which we get a signal and we have to react to it. And the signal turns out to be much more rich in information than the very simple ones that I showed you. It's not just a two-dimensional structure in terms of its content. It's actually, I can't remember, 3 or 4-dimensional. And it gives information about how to build a spaceship or a warp device that can get you to the location of the aliens. So I cannot say what would actually happen if we got a signal. I do know that it would probably build up from something very simple like, hello, I'm here, to a picture, to something much more complicated. And the hope is that what the aliens would want to send us is information of that type, information that shows us how to solve the puzzles of physics and technology, and maybe also information about the riddles of the universe. So Yuri suggested, of course, that we should send pulsar signals out because that shows how much we understand about pulsars and what the pulsars have been doing. But there's a lot of things we could potentially learn.
If you go back to the 1936 Olympics, I mentioned that's 80 years ago. Where's 80 light years from here?
Oh, it was off the graph when I was showing the local neighborhood, but it was not too far off the graph. The local neighborhood of stars. So the number of stars within that distance is not humongous. And the number of stars that could potentially respond to radio signals is not that big at this point. But it's increasing rapidly with time. And then there's the question of whether we are an interesting planet because people can see our oxygen, for instance, from afar. We may be a planet that other species would have noticed a long time ago and started broadcasting to. But it would take concerted effort on their part unless they've already heard a signal from us.
If a civilization 50 light years away had been sending out the same TV radio signals we have for 80 years, would we have detected them?
If they're close enough for us to detect them in the nearest 80 light years, I think the answer is possibly yes if we had pointed the Arecibo radio telescope at them. That's a distance within which I think we could actually get that signal.
So they would be strong enough, if they were identical to what we've been transmitting.
Potentially, yeah. If we're lucky in terms of timing, you have to be lucky not just in where you look, but also when, to see, like the sweep of a military radar type signal pass past you. Let me just ask if there's anyone in the room who's younger than 18 and they have a question. 18 is a pretty hard cutoff. No? Okay. Well, in that case, maybe we should limit it to just a couple more. Yeah. Okay. Yeah.
I seem to remember reading something long ago that NASA was the Kepler mission, and they reckon there's something like 300 billion stars in our galaxy, of which maybe 20 billion of the stars could be roughly the size of the sun, and around us there could be as many as 3 billion planets roughly have a zone of our stars roughly the size of the Earth.
Yep.
Can you believe that sort of figure?
Yeah.
The nearest one of those is so far away, forget about this. It's still a problem, isn't it?
If that were true, it would be a problem. But in reality, the numbers that you're quoting are not so different from the optimistic numbers bandied around in 1961 in the Drake equation.
Where they came from.
Yeah.
Well, that's what I read, but yeah.
So in fact, according to the Kepler satellite, we can't see all the habitable planets, but the trends make it look as though they're not so uncommon. So planets in general are very common. There's something like 5 per star, but then the habitable ones are significantly less common. But when it comes to the low-mass stars that are called M stars, the dwarf stars, they're dimmer, and the close-in planets are not boiling hot around them. They're more livable. Yeah, G-type stars like the Sun, the numbers are lower, but they're not zero.
The trouble is not the problem, as you said. It's the time thing. You might find a civilization a billion years ahead of us in evolution or a billion years behind us.
Yeah, if they're a billion years ahead, you have to wonder why they're not here.
We're going to take one final question over here.
Oh, okay.
What if the aliens can't figure out our signals?
That's an excellent question. Okay. So, that is an excellent question, and that is a real problem. What if they can't figure out our signals, or what if we can't figure out their signals? So this is what happens if we can't figure out their signals. Oh, what? Okay. That's you not figuring out my signal? This is what happens if they can't figure out, if we can't figure out their signals, then we don't even know that they're there, because we're looking for one type of thing, like radio waves, and they're sending us something else, like, I don't know, pieces of crumbs or something that ants would like. But if the aliens can't figure out our signals, then I think the way people think of it is that they're not the aliens we want to talk to, right? Because basically, we try to put our signals in the most understandable way that we possibly can. You following me? And so people work really hard to make signals that are as understandable as possible. It's like the opposite of writing a code. Like for a code, you want to write a signal that nobody can break except the person you're sending it to. But for these signals, you're doing anti-cryptography. You're trying to make a signal that pretty much only has one way to understand it. There's information you can get when you start to get close to show you that you've got it right, like you see the circle show up in the series of ones and zeros. And you reinforce the message over and over again in ways that build you up from a simple statement to something very complicated, which is not too different from the way you learned to speak English not that long ago, right? So it is possible. Okay, sounds like we have to stop.